This is Mark Anderson for Kellogg Community College. The Chapter 9 review test video starts now. We're going to start off today with looking at using compositions of functions, and I strongly recommend that you use this notation for the test. F of g of x, put them in together. You'll see that sometimes they'll use a little circle here, but I think this way is better for you. And when you see this, you're going to put the equation of g of x into f of x. So for the first equation here, what we're supposed to do is we're supposed to do f of g of 1, and I'll use the proper notation, well, not the proper, but just the way that I would like to see you use it, f of g of 1. And so what we're going to do is going to plug the 1 into the g, and then plug whatever that is into the f. So this is going to start off with g of 1. So we're going to take my equation here and put 1 squared minus 5. And so 1 squared minus 5, it really should look like a 5, is going to be negative 4. Then take that and plug it into my f, negative 4. So this makes negative 4 plus 4, and the answer there is 0. So my answer needs the correct notation. F of g of 1 is equal to 0. Now, letter B is going to do g of f of 1. So we're going to take our 1 and plug it in for my f, and then plug that into g. So I look at my equation right there. So f of 1 is going to be 1 plus 4. And 1 plus 4 is equal to 5. Then what I do is I'm going to take that 5 and plug it into my g. So my g of 5 right there is going to be 5 squared minus 5, or 25 minus 5, which is going to be 20. Okay, problem C. Problem C is going to be to take my equation, my g of x, and plug that into my f of x. So I'm just going to plug x into g, which is already set up, and then my g into f. So my g of x is g of x is x squared minus 5. Now what I'm going to do is plug that into my f of x. So I'm going to take my f and make it x squared minus 5. And so when I go to my equation, instead of 1, I'm going to write down x squared minus 5, and then I'll write my plus 4 after that. So this went into my f, and then I now have this answer. Now I do need to simplify it a little bit, so my f of g of x, again, you need to have that as your answer. It's the left side of your answer is going to be x squared minus 1. There's no reason to actually factor this into x plus 1, x minus 1, because this is the equivalent form of f of g of x. There's no reason to move forward with that at all. So now we have g of f of x. We're going to take my f of x and plug it in, my x, plug it into f, which is already done, then that's plugged into g. So this is going to be my f of x, which is x plus 4. That's equal to x plus 4. And so what I'm going to do then is take my g and plug my x plus 4 into every instance where it is there. So I'm going to have x plus 4 quantity squared minus 5. Now this is going to mean that I'm going to have to FOIL this out, which would make x squared plus 4x plus 16 minus 5. That's the FOIL of this binomial here, because it's x plus 4 and x plus 4. And this gives me x squared plus 8x, and then 16 minus 5 is going to be 11. And this is going to be what my g of f of x is. So again, this is what is on the left-hand side here. Whoop, whoop, whoop. And there's that there. Okay, so moving on to a similar problem. We're going to run through the same 4 steps for problem 2. And also I'm going to come here and get my graphing calculator ready. So let me go inside here, get my graphing calculator on. Alright, I'll move that off to the side so I can get it back later. Okay, so moving down to problem 2 and the rest here. Alright, so let's do f of g of 1. Oops, turn on my pencil. Bloop, bloop. Okay, so what we have here is what we have here is I didn't write anything. There we go, f of g of 1. So we're going to plug 1 into g and then that 1 into f right there. So what that's going to give me is it's going to give me, let's see here. It's going to start with my g of 1, so that's going to be 1 plus 2, and that's going to be equal to 3. So my g of 1 is equal to 3, and then we plug that into my f, so f of 3 is 1 over 3 squared. So my answer of f of g of 1 is going to be 1/9. Moving on to part B here, we're going to go my g of f of 1. And g of f of 1 is going to be equal to, let's see here, I'm going to take my f of 1 first, which gives me 1 over 1 squared, which is the same thing as 1. And by coincidence, g of 1 is going to be the same as what we did before here, 1 plus 2. So my answer for this problem here, which is going to be my g of f of 1, is equal to 3. Part C is going to be plugging my g of x into f of x. So my x is in g, which is already there, and then I'll put that into f. So I'm going to take my g of x, which is x plus 2, and then write in my f of x plus 2. So it's 1 over parentheses x plus 2 quantity squared. Whether you FOIL that out is your choice. I am going to FOIL this out just to show you my final answer. F of g of x is equal to the FOILed answer of 1 over x squared plus 4x plus 4. So 1 over that. Now D is going to be my g of f of x, where I'm going to have my x in for f, which is already done, and then put that in for g. So my f is going to be, let me think here, my f of x is 1 over x squared, and then I'm going to plug that in for my g, 1 over x squared. So I've got 1 over x squared plus 2, and therefore my g of f of x is 1 over x squared plus 2. Okay, now when you do problems 3 and 4, you're going to actually on the test compare the annual compounded interest rate versus continuous compounded interest rate. So when it says compounded annually, here's the equation you will use. And then if it says compounded continuously, you're going to use this equation. So put these in your little memory banks here, because here's how you would use it. $1,000 at 15% interest is going to look like this. A is equal to $1,000, because that's the principal, and then 15% interest, 1.15, because 15% plus 1 is 1 plus 0.15, so that's 1.15. And then you do that for the 0 power, then for the first power, the second power, and then the third power. Now, it's easy to do this on the calculator, and I'm going to show you how to do this and get your 4 answers quickly. It says be able to graph this. Now, I'm going to provide a graph on the test itself, but it's very important that you will graph them, and you'll see that they're pretty much going to look the same, but the numbers are going to be different. So your numbers for 3 and 4, or problems like these, will be very, very similar. Now, in this situation, we got compounded continuous interest, so the equation is going to be A is equal to 1,000, and the E and the rate is going to be 0.15, not 1.15, 0.15 times your time, so you're going to have that times 0, and you get your answer there, and then you'll do that times 1 and 2 and 1 and, I'm sorry, I put 1, 2, 3, but it really meant 1, 3, 4. And of course, these questions might be a little different on the test itself, but you should be able to quickly get your 4 answers and graph them. Now what I'm going to do, which is going to kind of erase all this on the screen, is to show you how to do this on the calculator. So let's turn this on and go to your y equals. To do the first one, you can type in 1,000, and then after that you're going to type in parentheses 1.15, and then caret x. Now, then you can go to the table, and you can actually see what the values are for this. Now, just so we can do 2 at once, I can also type in my 1,000, click on second natural log to get my e there, and then it's already put it in parentheses, which is kind of nice, so 0.15x. And then what this will do is I can go to my table now and get these values pretty quickly. So you can see that I can get my first year for both equations, my sorry, 0 time first year, third year, and fourth year, and you'll see that you'll actually make more if it's compounded, or your credit card company will charge you more if it's compounded continuously. And then you'll plot this on the same grid. They're going to look, I mean, on graph paper, this is going to look pretty close to each other because the graph paper is going to be going by thousands. But again, just a little graphing proficiency question before we get to the test. It's a pretty good idea. Okay, so let's go to the second page here. Let me kind of put this away and then move on to page 2. Okay, so this is a graphing section here. Page 2, I've got a lot of room for this, but again, kind of want to bring out the calculator to show you what you can do for this problem. Now, the first equation in these two problems is one that you can graph very quickly and easily. But you're not going to be able to plug log base 3 of x into the calculator. Most of your calculators are not set up to do that. So if I then hit graph, you can see what the line is going to look like, and then I'm going to go to the table and plot some, take some of these points on the table, and I'm going to choose some negative ones as well. Okay, so this is where I'm going to probably graph maybe from -2 to 2 or something. All right, so let's go plot from -2 to 2 for my first graph, because it says graph these functions and their logs on the same set of axes. So let's show you what that's going to be. So -2 is at 0.11111, so that's a tenth up, which is pretty small. -1 is at 0.33333, so about 33% up. 0 is at 1, and 1's at 3, and then 2's at 9, and then we're off the grid. So this graph is going to be, and I'm going to label this here, so I know on the test, you should label it so you can tell me what you're talking about here. But then what you do to graph the logarithm is you switch the x and y values. You can do so on paper if you want to, or just look at your calculator screen. So what this means is that my x is going to be at 0.1111111, and my y is going to be at -2. So that's plotted right there. Then my x is going, and again, it'll probably make sense if I just put a big x there, and I put a big y there, because this is going to be the logarithm, because logarithms and exponentials are inverses of each other. It looks like my x is 0.33333 and at -1. My x is going to be at 1 and y at 0. My x is going to be at 3 and y at 1. My x is going to be at 9 and y at 2. So here is my logarithm. And I call this a hook or a curve or a cat claw in class. It would not cross the y-axis, and also it's good to note that inverses graphically are reflections over this y equals x line. So an exponent and its logarithm are inverses, or they reflect over this y equals x line. Note the domain of this problem. The domain of this problem is going to be all real, but the range is where y is greater than or equal to 0. Not greater than 0, crap, not greater than or equal to, come on Anderson. Greater than 0, because it never touches the line. Now, look at the domain and range of this. Now, since they're inverses of each other, it kind of makes sense that they are flip-flops, because the domain is where x is going to be greater than 0, because it never goes negative, and the range is going to be all real. So you can kind of see the inverse relationship there, how their domains and ranges are inverses of each other. Graphically, they're inverses of each other as well. All right, move on to the bottom part here. Let me get my calculator back on the screen. Boop. And instead of 3 to the x, this is 4 to the x. So let's look at our table here. This is going to go off the screen more quickly than the other one. So let me graph -3 through 1. So this is for my y equals 4 to the x power. And if I'm graphing y is equal to 4 to the x, the first thing I'm going to start with is -3. -3 is this decimal point down there. -2 is 0.06. I mean, still just way flat. -1 is 0.25. So again, it's just so far down to the bottom you can't really see it. 0 is 1, 1 is 4, and then 2 is 16. So we're way off the screen. So there it is. Way off the screen there. It will probably go up more sharply than the picture I just drew. And then to graph the log, you're going to basically switch the x's and y's around. So this is going to be x This is going to be y because logs and exponentials are inverses of each other. So my x is 0.1 and I'm at -3. My x is 0.6 and I'm at -2. My x is at 0.25 and I'm at -1. Then finally 1 on my x is 0 on my y. And then 4 is 1. And then 16 would be 2, which is way off the grid. And now I'll try, oh shoot, it's hard for me to not want to cross that line. But again, a lot of the same things apply. This is the exponential with a domain that's real and a range where y is greater than 0. And this is the reflection line, y equals x. This is the logarithm of that line right there. The logarithm is the inverse of the exponential, so it reflects over the y equals x line, and the domain and ranges are also flipped, where x is greater than 0, and also the domain is real. All right. We're on a good momentum here. It's probably good to keep going here. Let's go to page 3. So let's see here. Boop. And I'll move this away. That might come back later. Okay, so let's talk about this. For each function, determine if it's 1-to-1, and if it's 1-to-1, find the formula for the inverse. Well, let's bring that calculator right back over here. And what we're going to do is use the horizontal line test to see if these are, in fact, 1-to-1. The first equation is going to be x cubed. So here we have x caret 3 minus 4. And the rule is if you have an odd power, you kind of have to check those, especially if they're greater than 1. Now it looks like this fails the horizontal line test, but it doesn't. It doesn't fail the horizontal line test because that actually doesn't flatten out. If we zoomed in, it would actually be continuously moving up, and there's only 1 pixel that flattens out, but that wouldn't violate the horizontal line test at that point. So 7 is 1-to-1. Let's look at the number 8 here. So we got x to the 4th power plus 2. Let's see if it's 1-to-1. And absolutely not 1-to-1 since it fails the horizontal line test. Okay, number 9. Let's go try that. 7 minus x. And let's delete the rest. Yes, it is 1-to-1, so that's good. And then finally, problem 10. Let's look at y equals 8. And wow, that fails the horizontal line test because it is a horizontal line. So, having done these 4 problems, 2 of which will be on your test, we see for part A that yes, it's 1-to-1 because of the horizontal line test. No, and which means that we can't actually find an inverse if it's not 1-to-1. Yes, it's 1-to-1, so we can find an inverse. And again, no, we can't find an inverse because it's not 1-to-1. So we really only have to do 2 of these 4 problems because 2 of them are not 1-to-1, therefore they do not have an inverse. So here's what we do. To find an inverse, what you will do is you will switch the x's and y's. So here's x equals y cubed minus 4, and we solve for y. So we add 4 to both sides, and then we take the cube root. So we have y is equal to the cubic root of x plus 4. Now I need your notation to be solid here. Your final answer should be f of -1x, which is the inverse of x, is the cubic root of x plus 4. Circle it. Alright, so I know where to find it, and you must have your answer written in terms of an inverse notation and not just the letter y. Okay, now number 9 is going to be just kind of like it was before, so let's take my h and let's go write it y equals 7 minus x. Switch the x and y around, and then solve for y. So we subtract 7 from both sides, and then divide by -1. If we divide by -1, what we get is -x plus 7, which is the same thing as this up here, so the inverse in itself looks exactly the same. So my final answer is going to be the inverse of h is -x plus 7, which, you know, kind of coincidentally is the same as this, because the inverse is a reflection and it actually reflects onto itself. Alright, let's do a little bit of simplification here. Now in this simplification problem, what we're going to do is we're going to see what these simplify to. Now in this problem, log base e is not written that way. Anytime you see log base e, you've got to write it as natural log of x. And anytime you see log base 10 of x, Don't write it that way, just write it as common log of x. So base e is natural log, base 10 is common log, and we don't put the 10 there, just like we don't put the 2 in the radical for square root. Now here, you have to think to yourself here, 3 to the what power is 9? The answer is 2. Now you have to think, 9 to the what power is 3? So you might be a little clueless on this one, or you might think the answer is negative, but it really is a decimal. So if you need some help here, use the change of base formula and go log of 3 divided by log of 9. The change of base formula will help you find out what this makes, and our answer here is 1/2 or 0.5, because the square root of 9 is 3. Here, the answer, 9 to the what power is 1, is 0. Anything to the 0 power is always going to be 1. Here, the answer is 1, because x to the first power is x. Here, the answer is 4, because 3 to the what power is 3 to the fourth power. Or you could just think to yourself of moving the 4 to the front, and then log base 3 of 3 is 4 times 1, which is 4. Now this one here was one of the classic problems we had in our worksheets. You can't actually say 3 to the what power is 50, because 3 to the third power is 27, and 3 to the fourth power is 81. So again, just another application of the change of base formula. So there's log of 50 divided by log of 3, and this gives you an answer of 3.56. And we spent a lot of time in section 3 and section 5 of this chapter dealing with the change of base formula and that idea. To round out the third page here, we are going to write some equivalent expressions, and we need individual logarithms of w, x, y, z, so we're going to split this up. And this is one that I want to do with you here, because this is going to be the log of base b of the numerator w squared x minus the denominator log base b of y cubed z. Now what makes this tricky is that when we do the numerator here, we'll just split these into the sum of two logs. So we have log base b of w squared plus log base b of x. Now we're going to have the sum of these two, but you're going to want to put this in brackets here because we're subtracting the sum of these here. So this is log base b of y cubed and log base b of z. Alright, now our first two, let's figure this out here. Move the 2 in front, so log base b of w plus log base b of x. Now here that 3 moves in front, so this is negative 3 log base b of y, and here's where people make mistake. This minus gets multiplied by this plus, so this is a minus log base b of z. So look out for that. This is a common mistake where people will put that as a plus, but you're distributing the negative to either of these binomials. This problem is actually a lot easier because this just breaks this up into log base a of x and then 2 log base a of y and then minus 3 log base a of z. Now what I did is 2 steps at once. Multiplication is broken up by addition, and then the exponents get to go in front of the logs rather than stay behind, as you'll notice that I did that with this problem here with the 2 moving in front, and this problem here with the 3 moving in front. Now what we're going to do for problems 21 and 22 is we're going to actually put these together. So you'll notice that these are being subtracted, so here we have log base a, and we'll have actually a numerator and a denominator where we're going to have w to the 4th power in the numerator. I know that just connected there, but just w to the 4th. And in the denominator, we got x cubed y, which is pretty darn cool. Now here you just push all these together, and this is going to be log base a of, and then pushing all these together would be 2x y squared, and then, ooh, you see the minus z to the 4th? That is going to put that into the denominator here, z to the 4th. Now the only kind of example I didn't put on here is something that has the number out in front, which would then put it up into the corner. So this second term could have been written as 2 log base a y, and this could have been written as minus 4 log base a z. All right, on to page 3, or 4, excuse me. Whoops. There we go. On to page 4. All right, a little bit of solving for x here. A couple of different ways to do each of these problems. In problem number 23, what I'm going to do for this is if you're struggling in this section, you're probably going to want to stick to the same process. So we want to get rid of the base of 2. So what we're going to do is we're going to drop log base 2 onto both sides here. Log base 2. And the log base 2 and the exponent of 2, they will simplify to 3x. And over here we've got log base 2 of 64. Now what I'm going to do here is use the change of base formula, or I can just think in my head 2 to the what power is 64. And whether you use the change of base formula, which is log of 64 divided by log of 2, you'll both end up with the answer of 6, because 2 to the 6th power is 64. The 3x basically waits to, see what happens. Divide both sides by 3. X is equal to 2. Now, if this problem went a little quickly here, I do all of these in the section 6 video, and I spend a lot more time going through them. So if you need more help doing these problems, I ask you to review the section 6 video for this chapter. All right, so what we're going to do here is we're going to do another log base 5 of both sides. So the log base 5 and the exponent of 5 simplify to x plus 2. And this just makes log base 5 of 15. Now I'm going to use the change of base formula to figure out what decimal that is. So log base 15 over log base 10 15 over log base 10 5, where the common logs divided, is going to give me x plus 2 is equal to the decimal of 1.68. Subtract 2 from both sides, x is equal to negative 0.32. Problem 25, we want to get rid of this 2 to the x power, so what we're going to do is just go log base 2 on both sides. So the 2's go away, and that leaves me with x, and on the right side is log base 2, 24. I'm going to use my change of base formula, because now this is really ready to set up and ready to go here. And so log base 24 divided by log base 2, x is equal to 4.58. Now here you might just say, oh, I want to just, get rid of this e, but the first thing you should do is divide both sides by 3. So now the 3's are divided, so 29 thirds is equal to e raised to the 2x power. Now to get rid of the e, we're going to not take the log of both sides, but we're going to take the natural log of both sides. Now the natural log and the e simplify to 2x, and the natural log of 29 thirds, if you type that into your calculator, gives you 2.27. Divide both sides by 2, x is equal to 1.13. Okay, moving on to the next problem, problems 27 through 27 and 28. Alright, so let's see here, got a couple more to go here. So what we're going to do in this problem is we are going to put the exponent down at the bottom here. So this is 5, taking everything to the base of the exponent. The 5 and the log base 5, they simplify, so I got 7 minus 2x is equal to 5 to the 3rd power, which is 125. Subtract 7 from both sides, so negative 2x is equal to 118. Divide both sides by negative 2. X is equal to negative 59. And normally we would look for answers when they became negative, but because you cannot have a negative log, but if I plug that negative 59 back into my problem, the minus 2 and the negative 59 would make a positive number, so this actually works in our answer. In problem 28, you cannot just take 10, 10, 10 under all of this. You have to get the logs together. You have to combine them. So let's move this together as to the quotient of x and x plus 7. And it's the quotient because they are being subtracted. Whoops. It should be negative 1, not negative 10. Alright, now I got ahead of myself because I was thinking, how am I going to get rid of common log? And you're going to basically put this as the exponent of the base 10. The 10 and the common log, since this is base 10 as well, they simplify, so I just have x over x plus 7. And 10 to the negative 1st power is 0.1. From here, we're going to cross multiply, or multiply both sides by x plus 7. So that gets multiplied over there, and x times 1 gets multiplied. So now I have x, or 1x, is equal to 0.1x plus 0.7. Subtract the 0.1 from both sides here. And this is 1x minus 0.1x, or a dollar minus a dime, is 90 cents x. And that's equal to 0.7. Divide both sides by 0.9. X is equal to, sorry, x is equal to 7 ninths, or 0.777777, 0.7 repeating. All right, 4 pages down, 2 pages to go. So let's go continue here. We're on a roll. No need to break up this video. Now, what I would do in problem number 29 is I would move this log on the right to the log on the left. That way we can consolidate this down to 1 log, so minus the log base 2 of x minus 3, minus the log base 2 of x minus 3. So that simplifies there. So here's what we have on the left-hand side. We've got the log base 2. Now, these are being subtracted, so that's going to make a quotient. A division problem, like so. Common mistake is people would just cancel out the 3's and write 2x, but that's not true. When you subtract logs, they become quotients of each other using the exponential rules, and that's equal to 4. So to get rid of a log base 2, we're going to put that into the exponent part of base 2. So those simplify out, and we have x plus 3 over x minus 3 is equal to 2 to the 4th power, which is 16. Cross multiply. So x plus 3 times 1 is x plus 3. 16 times x minus 3 is 16x minus 48. Then we subtract x from both sides. And at the same time, we can add 48 to both sides. So what we're doing is simplifying these to 0, simplifying these to 0. Well, it should be a 48. Okay, so this is going to be 51 is equal to 16x. Divide both sides by 16. And x is going to be equal to 3.4. This calculator, or this chapter allows you to use decimals, so please embrace that. Problem 30. Putting this together in the same log is going to be, and I'm going to use brackets here, this is going to be x plus 2 and x minus 7. And this is going to be log base 4 of 10. What this means is we got to get rid of these logs, so I'm going to basically have them in the exponent of base 4. Simplifies these logs, so now all I have left is x plus 2 and x minus 7, which I will FOIL in the next step, and that simplifies to 10. So let's FOIL this out. So x squared minus 7x plus 2x minus 14 minus 10 equals 0. I'm already just planning ahead to move that 10 to the other side because I'm going to probably factor this. X squared minus 5x minus 24 equals 0. And it is factorable. The two numbers that multiply to make negative 24 and add to make negative 5 are negative 8 and positive 3. Now, this gives me an answer of x is equal to 8 and x is equal to negative 3. Now, one of these answers doesn't work. If I plug my 8 into these equations, 8 plus 2 is 10, and 8 minus 7 is 1, well, shoot, actually that's okay. But if I plug the negative 3 into this equation, negative 3 plus 2 is negative 1, and negative 3 minus 7 is a negative 10. Sorry, can't have negative logs because of the domain restrictions. So problem number 30 has only 8 as our answer. We haven't been checking them because I'm pretty sure that plugging a positive into these equations is going to give us a positive, but in this case, the negative didn't work. All right, 3 more problems on this page. Really, 2 more problems and a warning to you. So here we have another situation where we have another plus, so what we're going to do is put these together using the log properties. If you put this and this together, it adds, so let's rock this out as, in a bracket, x minus 4 in parentheses and x plus 4 in parentheses. And that's equal to 2. Then, to get rid of all this, we're going to raise this to the exponent level and make our base 3, which simplifies that. That means our x minus 4 and x plus 4 will be FOILed, and I will do that in the next step. And 3 to the 2nd power is 9. 3 times 3. All right, so this is going to be FOILed to x squared minus 4x plus 4x minus 16 is equal to 9, and we can play this one of two ways. I want to do it this way. I'm going to add 16 to both sides. X squared is equal to 25. Take the square root of both sides, so x is equal to plus or minus 5. Now, from the warning before, if we plug the negative 5 back into this equation, we'll get negative logs, which is impossible. So our answer is only going to be 5. If you neglect the fact that when you take the square root, there's a plus and minus, and just write down the 5, you might get some points docked against you because you're accidentally or luckily getting into the answer without actually showing the work for it. So make sure you show your step and then commit to the positive answer. Just writing down, x squared is equal to 25 and x equals 5 and skipping this step may cause you to lose a point. For problem 32, we're going to combine the log base 4, and we're going to do this as a quotient because they are being subtracted. So section 4 of your work is basically reinforced here, and then we're going to put everything in the exponent of a base 4. So those go away. X plus 6, they go away. They simplify to 1, and then this makes x here. And this is 4 squared, or 4 to the second power, which is 16. So there we go. Then we crisscross multiply. X plus 6 is equal to 16x, because 1 times x plus 6 is x plus 6, and 16 times x is 16x. Subtract x from both sides. So we have 6 is equal to 15x. Then divide both sides by 15. And you should simplify this fraction, folks, because both top and bottom can be divided by 3. So this is going to be 2 fifths, or 0.4. Now, the warning here is what place values the hundredth, the thousandth, and the 10,000th. Be able to mark these correctly when entering log or natural log on your calculator. So the test is going to ask you to round to the nearest hundredth, the thousandth, or the 10,000th. And I just want to illustrate this, that after the decimal point, this is the 10th, the 2 is the hundredth, the 3 is the thousandth, and the 4 is the 10,000th. So tenths, hundredths, thousandths, tenths, hundredths, thousandths, 10,000ths. So this is the hundredth, this is the thousandth, this is the 10,000th. So make sure where it asks in the test to round to that location, you do so. Not doing so will have you lose a point. Okay, now please note that last problem is our story problem, and please note that any homework problem is fair game. Some test problems are not put into this practice test because they're considered to be general knowledge questions. So this test has roughly 90% of what's on the test, and I'm throwing an extra 10% onto the test to do the difference between my A's and my B's here. So there's one equation here that's not in this. See, the average credit card debt in 2010 can be calculated using this equation. So it's going to be my A is equal to 6,500. That's the average credit card debt, and this is a continuous growth equation, and it's going to be raised to the 15% times t. So that's the average credit card rate interest is 15%, and the average balance would be 6,500. So in what whole year would the debt go to grow over $10,000? So for part A, we're going to take this equation and type in 10,000 is equal to 6,500 times e to the 0.15 t, and we're going to figure out what that is here. So the first thing we're going to do is divide everything by 6,500 to get the e by itself, and that will give us 1.538. I think 3 decimals is appropriate here, and this is going to be e to the 0.15 t. And to get rid of the e, we'll just take the natural log of both sides. The natural log of e does simplify to 1, so this is 0.15 t on the left-hand side. The natural log of 1.538, or 1 and 538 thousandths, is going to be 431 thousandths. So we divide both sides by 0.15, and we get a t value that's approximately 2.87. So according, it says, in what whole year would the debt, if unpaid, grow to over 10,000? It would be in the third year, because it's closer to 3, and it would also be over $10,000 in the third year. Now it says here the doubling time for the debt in whole years, and it says to use the function in the calculator to estimate it, but you know what? It's just as easy to do this on paper as well. So the doubling time for 6,500 is 13,000 is equal to 6,500 e to the 0.15 to the t. Now divide both sides by 6,500. And we talked about this in some of our classes that the doubling time would always be 2 is equal to e to the 0.15 t regardless of what the starting value is. And half-life would be 1/2 equals e to that growth rate. Again, that's talked about in class. I'm not going to spend more of our time here to elaborate. But then what you're going to do is take the natural log of both sides. Natural log, natural log. Natural log of e simplifies. So 0.15 t is equal to the natural log of 2, which is 693 thousandths. Divide this by 0.15. And then what we're going to have is our t in terms of our doubling time. So 4.62 is when we divide these. So in 5 years, the the $6,500 debt that people have on their credit card is going to double to $13,000. So if you have a 15% interest rate, it doubles in under 5 years, or about 4.5 years. All right, well, thank you for skimming through this video and seeing the things you need to see. Good luck on the test.